And then, okay, should be recording now. So I want to do this one algebraically also because I know there's some on the sheet that are very similar to this that I want you guys to be able to do algebraically. So if we're looking at the function absolute value of x over x, and we want to find the limit as x approaches 0 from the left, what can you tell me about all of the x values that we're interested in?
They're -1.
They're all well, yeah, they're all not the values of f of x, but just the values of x. If we're approaching 0 from the left, all the values of x are negative values, right? This is x is always less than 0 when we're approaching 0 from the left. Would you all agree with that?
Yeah.
Okay.
Yep.
So what can you tell me about absolute value of x if x is less than 0? What does the absolute value of x equal?
X.
A positive number, or just x?
It equals it equals a positive number, but it's not just x, right? Because x is already negative, and so the absolute value of x is actually the opposite of x. You guys all agree with that, or no?
Yes.
Yes. Plug in any x value. Plug in -7 to the absolute value of x, right? We say if x equals -7, absolute value of x is 7, right? It's the opposite of what x was. So the way we could rewrite this then, if we're talking solely about the limit as x approaches 0 from the left, that means that we know all of the x values are negative, which means that we are really looking at the limit as x approaches 0 from the left of the opposite of x over x, which simplifies down to what? Should simplify down to -1, exactly. And so this limit is just -1, which we're going to talk about today. The limit of just a constant is just that constant. Okay? And the limit of as x approaches 0 of -1 is just -1. What about when we do it from the right-hand side? When we do it from the right-hand side, the absolute value of x, since all the x values are positive, absolute value of x is just equal to x. And so this becomes the limit as x approaches 0 from the right of x over x, which is just 1. X over x is 1, and the limit as you approach any number of 1 is just 1. Does that make sense? Does that help for, I know a couple of you guys were asking me about how to do some of those algebraically the other day. So hopefully that helps. You should be able to apply that same idea to the ones on that assignment that I gave you guys. And since those aren't the same, according to our rule from the other day, that doesn't exist. Sound good?
Why do we have to do this absolute value thing again? Can we just see it from the graph that, oh, we can see that it's just approaching -1 from the left side and then +1 from the right side?
Yeah, so you can definitely just see it, but sometimes on the AP tests, they're going to ask you for an algebraic explanation of why, especially on a free response question. They might say, like, show why this is -1 or 1 without using the graph, something like that. So you need to be able to do it either way. All right, so we're going to move on. We're going to take a look at this one. And I want you guys to real quickly just graph this piecewise function. And then we're going to look at these limits. So take a second to graph it on your own. All right, so for x less than 1, we have 3 minus x. So 3 minus x should look like, well, that's not very good, but it should look something like that for x less than 1. And when x less than 1, not less than -1, something like that. And then should be at x equals 1, we should have the 0.4, and x squared plus 1 when x is greater than 1. So x squared plus 1 looks, let's see here. Should have an open circle here and just be going up like that. I guess my graph's not very good because I'm drawn on a laptop screen, but should be, this should be sort of parabolic looking over here. This should be linear over here, and I got that single point that's an outlier. Everybody agree with that? Okay, cool. So we're going to do this algebraically and we're going to do it graphically. Both of them should be pretty straightforward. As we approach 1 from the left, which piece of our piecewise function includes only values that are less than 1?
First
Should be
piece.
the first piece, right? The 3 minus x piece. So all we got to do is throw in 3 minus 1, which gives us 2. And if we're looking here, we can see that as we approach 1 from the left, yeah, we're approaching that hole that we have there at 2. We are approaching that discontinuity. And remember again that the point that's there at x equals 1, y equals 4 doesn't matter for the limit because it's what we're approaching. Everybody go with that?
Yeah.
Okay, cool. And
Yep.
then as we approach 1 from the right, the piece of our function that we're looking at is the x squared plus 1, because those are the values that are greater than 1. So it should be just 1 squared plus 1, which gives us 2 again. We got 2 here, we got 2 here. And if we look graphically at it as we approach from the right, yep, we're approaching 2. And therefore, what does that tell us about the two-sided limit? It ought to also be 2. Easy enough?
Yeah, so this is how you'd be solving it algebraically, right?
Yeah, so algebraically would be, what I wrote over here. And we just kind of looked at it and said, yeah, it's going towards 2. And yep, it's going towards 2. If we just look at it. So. Good?
Yep.
All right,
Yep.
cool. All right, so what I was mentioning earlier is the limit of a constant is a constant, always 100% of the time. So if I say the limit as x approaches a of some constant, it's always whatever that constant is. The limit as x approaches 3 of 7 is 7. The limit as x approaches -4 of 10 is 10. The limit as x approaches 7 of pi is pi, right? The limit as x approaches 1,000 of 0 is 0. The limit of a constant, no matter what you're approaching, is always a constant, which should make sense because a constant is just, it's just a horizontal line, right? Here's 7. My constant is 7. No matter what I'm approaching, if I'm approaching 3, it's still 7. As x approaches 3, the value is still 7. As x approaches, 100, it's still 7. Okay. Easy enough. The limit of a constant is a constant. Everyone good there?
Yep.
All right. We're going to just run through some nice, simple, easy rules here. Here's a few more. These are all things we're going to need to know and be able to apply. So if you're writing stuff down, you're going to, if you're writing down rules for limits that you need to know, make sure you write all of these ones down. And we'll talk about them in a second. Read through them, and then we'll talk about what each of them mean and take a look at them a little bit. So the first one we're talking about here is if we have two different functions that are being added together, and if we're looking for the limit as they approach some value, you can separate the functions out and do each limit separately. Second one's just saying that if I have two functions being multiplied together, like let's say, for example, I have the limit as x approaches 3 of 2x. Well, that's two different functions being multiplied together, right? That's the function 2, and it's the function x. So I could, if I wanted to, rewrite this as the limit as x approaches 3 of 2 times the limit as x approaches 3 of x. Right. Now, in this case, you wouldn't need to do that. You could just plug that in because it's a continuous function, but there'll be some functions where you need to actually separate them out, which we'll see later today. We could do the same thing with division, provided that the 1 in the denominator doesn't equal 0, because if the 1 in the denominator equals 0, then obviously that's a problem because you can't divide by 0. Skip down to the bottom one, you can do the same with subtraction. And then this one right here is very important. It doesn't seem that important right now, but if I have the limit as x approaches 3 of a constant times a function, let's say x squared, I can take the constant that's in front of that function and pull it outside of the limit. So I can call this 2 times the limit as x approaches 3 of x squared, which in this case doesn't seem that exciting because we know that 2x squared is a continuous function. I can just plug the 3 in and square 3 and get 9 and multiply by 2 and get 18. What's the point of bringing the 2 out? Well, there is no point. But there's going to be some instances where we're dealing with trig functions where this is exceptionally important, and we're going to have to use this rule quite often. Any questions on those few rules right there? All right, next couple here is if we have an exponent, so x to the n, it's always just going to be a to the n for any positive integers. And even more importantly than that, if we have a full function, let's say this is sine x to the 5th power that I'm taking the limit of, I can take just the limit of the function, so just the limit of sine x, and then raise the value to that 5th power. Okay. So this one down here can be rewritten if we want to as the limit as x approaches 2 of 3x plus 4, and then raised to the 5th power. And once again, that doesn't seem like it's super useful at this point, but when we start dealing with trig functions, it's going to be very useful. Simple, basic, easy rule. We can do the same thing with roots. So if we taking the nth root of something, we can pull those roots and those powers outside of the limit if we want to. I'll leave it here for you to read that if you want for a second, but that's basically the same as what we did with the power functions. If you have any questions on this as you're reading through it, let me know. So see if you can evaluate this limit. You should be able to. It should be easy. Using some of those rules if you want to, or you can just straight plug it in and see what you get. That's what I would do. I'd just plug it in and see what you get. So if we plug in the 8, what's 8 to the 2/3 power?
4.
4, right? Cube root of 8 is 2, squared is 4. plus 3 times root 8, and root 8 is the same as 2 root 2, over 4 minus 2. So we've got 4 plus 6 root 2 over 2, which is just 2 plus 3 root 2. Easy enough. All this limit stuff is pretty easy until it gets more difficult. Everybody feeling okay so far? Anybody having issues? All right, now we're going to start making it a little bit more difficult. A little bit. This is called the Sandwich Theorem, also called the Squeeze Theorem. And it is actually lately, the last couple of years, it's been showing up on the AP test a little bit. It hadn't been for a long time before that, so we're going to make sure we have a good understanding of this. It's used to prove one really important limit that we talked about earlier yesterday, and some other ones that we're going to deal with first as well. So the Sandwich Theorem says that if I have one function, and we're going to call it h of x, that is sandwiched between two other functions, f and g. Okay? So note in the picture, we've got h is sandwiched between f and g, right? As in h is always less than or equal to g and always greater than or equal to f. And if we know that the limit as x approaches some value a of f of x is equal to the limit as x approaches a of some other function g of x, the one that's above, then that means that the limit as x approaches a of the one that is sandwiched between them has to have the same limit. Does that make sense? I think the picture helps sort of illustrate that. G is always above h, f is always below h, and g and f happen to have the same limit at a, so h must have the same limit at a. Everybody see that and feel okay about that? You're all still there?
Yes.
All right, if everybody feels okay, then we're going to move on and we're going to start dealing with it. So we are going to use that theorem to prove that the limit as x approaches 0 of x squared times the sine of 1 over x squared is equal to 0. Before we start trying to prove it, though, we're going to actually take a look at what that graph looks like in Desmos. So let's do that real quick. We've got x squared sine of 1 over x squared. All right, I'm going to zoom in a little bit on it. You guys can all see Desmos now, yeah?
Yeah.
All right, cool.
Yep.
This is what that graph looks like. So it starts oscillating, it kind of comes in here, starts oscillating back and forth, but it's narrowing out. So it's similar to the sine of 1 over x function that we looked at the other day. But instead of oscillating up to 1 and down to -1, it looks like these oscillations are getting smaller and smaller and smaller as we get in here. Right? Looks like they're approaching 0, even though it's oscillating probably an infinite number of times. They're getting smaller. It's kind of an interesting looking graph. So let's see, we'll leave it right around there. We're going to come back to looking at this graph in a bit. But what we need to do is we need to figure out, since we can't figure out what this limit is without some other method other than just plugging in numbers, because if we just plug in numbers here, if we just plug in our 0, we end up with 0 times the sine of 1 over 0, and the sine of 1 over 0 we can't do because 1 over 0 is undefined. And even though it's 0 times something that's undefined, we can't just assume that that's actually 0, unfortunately. 0 times infinity is an indeterminate form, just like 0 over 0 is. So any thoughts on what we can do with this?
Split up the x squared and sine.
Using the formula from before, so something like the limit as x approaches 0 of x squared times the limit as x approaches 0 of sine of 1 over x squared. Is that what you mean?
Yeah.
All right, that's a good thought. So let's do it what we can with that. This becomes 0, right? If we plug in 0 to x squared. But over here, when we multiply this by this one, we end up with the sine of 1 over 0 still. And what is the sine of 1 over 0? Well, as we're approaching 0, this value, this keeps oscillating back and forth, right? Because if we approach 0, this gets very small, which makes the whole fraction get very large. And so as we go towards infinity, what is sine doing? Well, as we go towards infinity, sine is just oscillating back and forth. And so there's no set number for this. And so we don't have if we don't have a set number, if we have something that we can't find a value for, we can't multiply it by anything, even if it's 0, unfortunately. So it's a good idea, but it doesn't end up working out in this case. Any other thoughts?
Could you line like 2 lines that go like that follow the curve of like the oscillations, like one on the top, kind of like following the oscillations, and then one on the bottom, like curved lines.
Okay, so you'd like to find something, we'll go back to the graph for a second, something that follows this curve right here?
Yeah.
Okay, and something that follows this curve right here. So something that's going to make, that's always going to be above this and something that's always going to be below this. Is that what you're saying?
And then find their limits.
Okay, and then find their limits. That's an excellent idea. So let's see if we can make that happen. What do we know about this second piece of this function, the sine of 1 over x squared? What can you tell me about that? Tell me anything you can tell me about it. Just that one little piece of it.
And it's always going to be positive.
Sine of 1 over x squared is, okay, so the 1 over x squared part's always going to be positive, but is the sine of that always going to be positive?
Oh, yeah, I see what you mean.
Not always. The 1 over x squared is always positive. I agree with that. Well, what happens when you, okay, what can you tell me about 1 over x squared? It's a number, right? It's a positive number. True? What happens when you take the sine of a number? What do you get?
A number between 1 and -1?
A number between 1 and -1. That's correct. Always between 1 and -1. True? Would you guys agree with that?
Yeah.
That's the range of sine, right? I mean, we
Yeah.
go into the graph of sine and we take a look at it, and it's always something between 1 and -1. Right? It never goes above 1. It never goes below -1. So this is starting to look a little bit like this sandwich theorem, right? I have to have a function less than or equal to another function less than or equal to another function. But I want to have the full x squared sine of 1 over x squared in the middle, and I don't. So how can I solve that problem? How can I get an x squared in there?
You multiply everything by x squared.
Multiply everything by x squared. What's that going to give me? Negative x squared is less than or equal to x squared sine of 1 over x squared is less than or equal to x squared, which, I mean, should be true, right? If I multiply all 3 pieces of this inequality by the same exact thing, I should still have another true inequality. So let's go back and take a look at the graph here, and let's throw in x squared and negative x squared. And if we zoom in a little, we can see that these oscillations are hitting x squared and then hitting negative x squared and then hitting x squared again and then negative x squared, and they're going to keep doing that infinitely. And this function, y equals x squared, is an upper bound for the function we're interested in. And the function y equals negative x squared is the lower bound for the function that we're interested in. Everybody see that?
Yeah.
All right. So now that we've got that, we can use the sandwich theorem and say that if the limit as x approaches 0, because that's what we're looking for, of negative x squared is what? What is that limit?
0.
0. And if the limit as x approaches 0 of positive x squared is the same, which it happens to be, it's 0, right? Then that means by the squeeze theorem or the sandwich theorem, the one that's stuck between them, the limit as x approaches 0 of x squared sine 1 over x squared is also equal to 0. Any questions on that? Does that make sense? That's the basic idea of how the sandwich theorem works. You develop one function that's above and one function that's below, and you find those limits. All right. I need to quickly step away because apparently my dog puked all over the floor and I need to clean it up. Sorry. So why don't you guys see if you can figure out a way to do this one on your own, and I'll be back hopefully in like 2 minutes after I'm done dealing with this horrible thing before she eats it. All right, I'll be back in a sec. Do this. All right, sorry about that. Averted the crisis. I got 2 dogs. The problem I have is, you don't want to know the problem I have with my dogs, but I'm going to tell you anyway. Let's see. The one dog has medical problems and she has difficulty digesting her food. She has to take some medicine for that. So she has like constant diarrhea. And the other dog likes to try and eat it, but then she pukes it back up. And then when she pukes it up, the other dog tries to eat it because she hasn't had her medicine, and then she has more diarrhea. It's really unpleasant, but it's kind of like the circle of life, you know? It's like one dog pukes it up and the other one diarrhea, and then we just like, you know, I don't have to buy them food or anything because they just feed each other. It's really fun. Yeah, it's good times. You should definitely own dogs. All right, back to math. So if anybody needs to take a break to go and puke after hearing that, I understand, but let's do this problem. What can you tell me about the cosine of 1 over the cube root of x? Anybody? What can you tell me about that?
It's always between 1 and -1.
It's always between 1 and -1. Same thing as before, right? And if I just want to multiply everything by x to the 4th, this is essentially the exact same problem as we were dealing with a minute ago, except with a little bit different function. We can sandwich our function between -x to the 4th and x to the 4th and look at the limit as x approaches 0 of -x to the 4th, which is 0. And that is the same as the limit as x approaches 0 of positive x to the 4th. And so by the squeeze theorem, the limit as x approaches 0 of x to the 4th cosine of 1 over the cube root of x is also equal to 0.
Are you multiplying by x to the 4th because the original limit has x to the 4th in it? Is that why you're choosing to multiply by x to the 4th?
Exactly. That's exactly right. Yep. If I had an x to the 6th in there, or, you know, an absolute value of x, I'd just multiply each of them by that and see if it worked out. If it works out, then great. If it doesn't, then you're going to have to try and find another way. But 99.9% of the time, it's going to work out pretty nicely like this. Good?
Yep.
It's better than cleaning up dog vomit, right? So, all right. Now we got one more this one looks exactly the same, but it's a little bit different. And we're going to have to figure out a way to deal with this one in a slightly different way. Any thoughts on this? Nobody?
Isn't x cubed can also equal to negative?
Yeah, that's the problem. So we can start this off the same way, right? We know that the sine of 1 over the cube root of x is always less than or equal to 1. It's always greater than or equal to negative 1. But when I try to multiply both sides of this by x cubed, sometimes x cubed is positive, and sometimes x cubed is negative, which creates a problem when we're dealing with inequalities, because sometimes when we multiply everything by x cubed, the signs don't need to flip because x cubed is positive and we're multiplying by a positive. But sometimes when we multiply by x cubed is negative and the signs need to flip. So we got to do two different cases. One where we multiply by a positive x cubed, which gives us negative x cubed is less than or equal to x cubed sine of the 1 over cube root of x is less than or equal to x cubed. And on the other side, when I multiply by x cubed, what has to happen? When x cubed is less than 0, I need to flip my inequality signs. Everybody see why I need to flip the inequality signs there?
Multiplying by a negative?
Multiplying by a negative, that's exactly right. Okay. So now I've got two different inequalities, but they both sort of work with the sandwich theorem, right? I still got the function I want sandwiched between two other functions. Just in one case, my function is always greater than the negative and less than the positive, and in this one, it's always less than the negative and greater than the positive x cubed. So when we go in and find the limits of the left function here, negative x cubed, and the right function here, positive x cubed, as I'm looking at the limit as x approaches 0, can I do a limit as x approaches 0 for this? The answer is no. I can't just do a limit as x approaches 0. Why not? If x cubed is positive, that means that x is positive. Would you all agree? Cube a positive number, you get a positive number.
Yeah.
You cube a negative number, you get a negative number. True?
Yes.
If x is only positive for this inequality, if this inequality is only true when x is positive, I can't approach 0 from both sides because the x values are only positive. So I can only approach 0 from which side?
The right.
From the right-hand side if the x values are positive. So we're going to approach 0 from the right of negative x cubed, which is 0. And we're going to approach 0 from the right of positive x cubed, which is also 0, which should tell us that the limit as x approaches 0 from the right of x cubed sine of 1 over the cube root of x is also equal to 0. And on this side, when we're doing the x cubed is less than 0 part, what are we going to have to do? We're going to have to do a limit as x approaches 0 only from the left. And so the limit as we approach 0 from the left of negative x cubed is 0, which is the same as the limit as x approaches 0 from the left of positive x cubed, which tells us that the limit as x approaches 0 from the left of x cubed sine of 1 over the cube root of x is 0. And now, because the right-hand limit is 0 and the left-hand limit is 0, our rule from before that says if the left-hand limit is the same as the right-hand limit, that means that the two-sided limit exists and is the same. We can say the limit as x approaches 0 of x cubed sine 1 over cube root x is also equal to 0. So it seems a little bit tedious and like a little bit of extra work, but that's kind of the way we got to go, because otherwise we're doing things that aren't accurate. We can't just not flip the inequality signs for half of our x values, so we got to split into two cases. And we can't do a two-sided limit for either of these because we split our x values right in the middle for positive x's and negative x's. Good or no?
Good.
All right, spectacular. Let's see. Trying to decide here. I think what we should do is we should stop here. We should deal with this one tomorrow. I think we should stop there. And if you have any questions on anything from your assignment or anything that we've done so far, I think you should ask. And then we should be able to get through the rest of this in Thursday and Friday and basically be done with limits this first week of school. First real week of school. So I think we're going to stop right there. Does anybody have any questions on